Quantum Physics Unlocked, The Secret, Reality Isn't Real. Reality is a lie you've been believing your whole life, and quantum physics holds the secret to this mind-blowing truth. Look around you, a solid table, a sturdy chair, the floor beneath your feet. Our everyday experience tells us that the world is made of definite, tangible things with predictable behaviors. A ball you throw follows a clear path. A car moving at a certain speed will cover a predictable distance in a given time. This is the world described by classical physics, the physics of Isaac Newton, a world that makes intuitive sense to us. But what happens when we zoom in, way in, to the fundamental building blocks of everything? What are the tiny particles that make up the atoms, that make up the molecules, that make up the table, the chair, and you? This is where reality takes a decidedly weird turn, a turn that is stranger than fiction. Welcome to the quantum realm. This is the world of subatomic particles like electrons, photons, particles of light, quarks, and neutrinos. At this incredibly small scale, the rules we are familiar with no longer apply. Instead, reality seems to behave in ways that defy our intuition and challenge our common-sense understanding of how things should work. Throughout this series, Quantum Mysticism, where science meets spirit, we will explore the mind-bending discoveries of quantum physics and see how they resonate with ancient spiritual teachings on consciousness, interconnectedness, and the nature of existence. But before we can draw those fascinating parallels, we first need to get a grasp, however simple, on the fundamental weirdness of the quantum world itself. This first episode is dedicated to explaining some of the core concepts of quantum physics in the most accessible way possible, without needing a science degree. We'll explore three key ideas: waveparticle duality, superposition, and entanglement. Think of this as laying the groundwork, planting the seeds of curiosity about a universe far more mysterious and interconnected than it appears on the surface. The everyday world versus the tiny world. Imagine you're playing a game of billiards. You hit the cue ball, and it travels across the table, bouncing off other balls or the cushions according to precise, predictable laws. You know exactly where each ball is at any given moment, and if you know the forces involved, you can predict exactly where it will be in the future. This is classical physics in action, a world of definite locations, predictable trajectories, and clear properties. Objects are solid, distinct, and behave in reliable ways. Now, shrink down, past the felt of the table, past the wood, down to the level of the atoms that make up the balls, and then shrink further into the atoms themselves, looking at the electrons whizzing around the nucleus, or the photons of light bouncing off the surface. At this scale, the billiard ball analogy falls apart completely. The tiny constituents of matter and energy do not behave like miniature billiard balls. They don't have a precise location and a definite path in the same way. Their behavior is governed by probabilities and seems to be influenced by the very act of observation. It's like trying to play billiards, where the balls sometimes act like ripples on a pond, can be in several places at once, and are mysteriously linked to other balls regardless of distance. This is the quantum realm, a world where discreteness, chance, and interconnectedness replace the certainty and separation of the classical world. Or particle, why not both? One of the first and most mind-bending discoveries in quantum physics was the concept of wave-particle duality. In our everyday experience, things are either one or the other. A wave is like a ripple on water or a sound wave traveling through air. It's spread out, it interferes with other waves, and it doesn't have a definite location. A particle is like a tiny grain of sand or a dust mote. It has a definite location, a definite mass, and behaves like a tiny, localized object. They seem fundamentally different. However, at the quantum level, things like photons, particles of light, and electrons, which make up atoms, don't fit neatly into either category. They can exhibit both wave-like and particle-like properties depending on how you observe or experiment with them. The most famous illustration of this is the double slit experiment. Imagine you have a barrier with two narrow slits in it, and you shoot tiny particles, say electrons, at the barrier. If electrons were just classical particles, you'd expect them to go through one slit or the other and create two distinct piles on a screen behind the barrier, right in line with the slits. like shooting tiny marbles through two gaps. You get two concentrated lines of marbles on the other side. But that's not what happens when you shoot electrons or even photons at the slits. Instead, you get an interference pattern on the screen, a pattern of multiple bright and dark bands, just like you'd get if you shone a wave, like light or water ripples, through the two slits. A wave passing through two openings spreads out and interferes with itself, creating crests and troughs that result in areas of high intensity, bright bands, and low intensity, dark bands, where the waves cancel each other out. The electrons, seemingly acting as individual particles when they hit the screen, they arrive as discrete points, somehow behaved like waves on their journey, passing through both slits simultaneously and interfering with themselves. What's even weirder? If you try to detect which slit each individual electron goes through, the interference pattern disappears. The mere act of observing or measuring which path the particle takes forces it to behave like a classical particle, going through only one slit, and you get the two simple bands expected from particles. When you're not looking, it acts like a wave. When you look, it acts like a particle. This isn't just about our ignorance of which path it took. It's about the nature of reality itself at this scale. Particles don't have a definite position and momentum simultaneously until they are measured. They exist as a sort of fuzzy potential until pinned down by observation. This duality suggests that the fundamental nature of reality is not fixed and solid in the way our everyday experience leads us to believe. It's more fluid and depends in some strange way on how we interact with it. Existing everywhere at once, the idea of superposition. Building on the strangeness of wave-particle duality is the concept of superposition. In classical physics, an object is in one definite state at any given time. A light switch is either on or off. A coin is either heads or tails. But in the quantum world, a particle can exist in multiple possible states simultaneously until it is measured or observed. Imagine that light switch, but instead of being simply on or off, it's somehow both on and off at the same time. Or imagine a coin spinning in the air. Before it lands, it has the potential to be heads or tails, but it's not definitively one or the other until it stops. Quantum superposition is stranger than that. It's not just that we don't know the state. The particle is actually in all its possible states at once. An electron, for example, can be in multiple locations or have multiple spins, an intrinsic property, at the same time. A famous thought experiment illustrating this, though often misunderstood, is Schrödinger's cat. Imagine a cat in a sealed box with a device that has a 50% chance of releasing poison based on the state of a quantum particle, say if a radioactive atom decays. According to quantum mechanics, until the box is opened and the system is observed, the atom is in a superposition of both decayed and not decayed states. Because the cat's fate is linked to the atom, the cat is, in this theoretical superposition, considered to be simultaneously both alive and dead. It is only when you open the box and observe the cat and the atom that the superposition collapses, and the cat is found to be definitively either alive or dead. This concept is deeply counterintuitive. It suggests that reality, at its most fundamental level, exists as a realm of potentiality. A quantum particle doesn't have a single definite reality before it's observed. It exists as a combination of all its possibilities. It is the act of measurement or observation that seems to force the particle to choose one definite state out of the many it was simultaneously occupying. The question of exactly what constitutes an observation or measurement that collapses the superposition is known as the measurement problem in quantum mechanics and is one of the deepest unresolved mysteries in physics, hinting at a potentially profound role for consciousness or interaction in shaping reality. Spooky action, the mystery of entanglement. Perhaps the strangest quantum phenomenon of all is entanglement. This occurs when two or more particles become linked in such a way that they share the same fate, no matter how far apart they are in space. When particles are entangled, they are described by a single quantum state. If you measure a property of one entangled particle, like its spin or polarization, you instantly know the corresponding property of the other entangled particle, even if it's on the other side of the galaxy. Thank you for watching, and if you subscribe, you will not miss part 2 of this series. Until then,